Let's start, yeah.
Okay. So this is the second lecture about homotopy spheres, and last time we just talked about, in general, about surgery theory and about the surgery exact sequence, and we finished by seeing or having this surgery exact sequence for the sphere, for an n-dimensional sphere, and so I will just recall some stuff today, and then I will just recall some stuff now, and then we will move on to to calculating this ability group. So just to remind ourselves, so a homotopy sphere is a manifold. A homotopy n sphere is an n-dimensional manifold, which is homotopy equivalent to the standard sphere Sn. And from the Poincare conjecture, in the topological case, we know that therefore that it is also homeomorphic, automatically homeomorphic to the standard sphere Sn, but not necessarily diffeomorphic, because the Poincare conjecture doesn't hold in the smooth category necessarily. And so what we wanna do is to classify those homotopy spheres up to diffeomorphism in some sense. And this is what this group allows us to do. And last time we ended we obtained this long exact sequence of actually groups. And just let me go through the terms in this group very quickly, and then we will move on to the calculations. So, just to remind, I think because I was not here last time. What we are trying to do, we will not be calculating this group directly. We will change this problem, which is some kind of geometrical problem, into a problem of homotopy theory. So, we will see that it is equivalent to learning some stuff about the so-called J homomorphism, which is some map in homotopy theory. So from some homotopy groups to other homotopy groups. Okay, so we have this long exact sequence of groups, and which are the terms. So this is the term. These are the terms that interest us the most, and these are the abelian groups of orientation preserving diffeomorphism classes of oriented homotopy spheres. Then we have the normal invariants of Sn, and we saw that for the normal invariants we have two different interpretations. So we can view them either as some normal cobordism classes of degree 1 normal maps, where a degree 1 normal map is a map from a closed smooth manifold M to the n-dimensional sphere, which is covered by some bundle data. So, which is covered by a bundle map from the normal bundle of this manifold stabilized to some bundle over Sn. And those degree 1 normal maps are put into normal cobordism classes. So if we have some normal cobordism between them, they belong to the same class. And we saw that we can view those pairs of manifold map as like a collection of pairs on which we do some geometric procedure, which is called surgery, in order to obtain a homotopy equivalence. And then these normal cobordism classes correspond to some surgery orbits. So we can move into one class among these manifolds by doing surgery. Okay, and then I talked about the fact that we have a second homotopy theoretic interpretation of normal invariants. So actually we have some classifying space for those normal invariants. So a space which is called G mod O, such that the normal invariants are in bijection with the homotopy classes of maps from the standard sphere to the space G mod O. And where, I want to continue this, where we saw that G mod O was actually the homotopy fiber of some map J bar in here. So, in other words, a space such that this is a fibration, where this is a fibration. Okay, and the last term we have here are some L groups. So these are groups where, okay, so the L groups.
I think we don't really want to know the definition. We don't need to recall the definition now. I think we just want to know that they are like that. Okay, so or
yes, so the definition is just here, but Sergey will talk about it. The important thing is that we know them for the case of Z, and in the case of Z, the L groups are 0 in the odd dimensional cases, Z in the 0 mod 4 case, and Z mod 2 in the 2 mod 4 case. And the isomorphisms are actually given by, so in the 4k dimensional case, the isomorphism is given by taking the signature of some quadratic form, dividing it by 8. So it's this, yeah. And in the 2-dimensional case, it's given by something that's called the Arf invariant.
and I mean you can say that it's not just some quadratic form. It's really the signature of M.
Yeah, and so
right. So and
yeah,
that we know what it
I
is.
wanted to, in that, lastly, I want maybe to mention this map, which is what I call the surgery abstraction. And okay, I will get to it. Or yeah. Okay, so we have this long exact sequence of groups, and now let's look at what happens. And first, let's look at what happens in the odd dimensional case. So odd dimensional case, so n is either 1 or 3 modulo 4. Okay. I will leave this sequence. And so from this sequence and these isomorphisms, we can actually see that the long exact sequence is split into some short exact sequences of this form. So right. So what's important in the odd dimensional case, that these L groups on the right of the group that we are interested in will always be 0. This is the 0 here. And so that means that we get such a short exact sequence just where this term is just the kernel of this map. Right?
Yeah, it's some strange -1 there.
Oh, sorry. Is that right? Yeah. So it's the kernel of this map, and so what this sequence actually tells us, let's see what the problem is. So first of all, it tells us that the surgery exact sequence is always, the surgery abstraction is always 0, right? So any degree 1 normal map we have actually comes from this group here. So actually any degree 1 normal map can be transformed by some surgery steps into homotopy equivalence. By a finite number of surgery steps. Into homotopy equivalence. But the problem is that we may have two classes in here, so two diffeomorphism classes of homotopy groups that actually correspond to the same normal cobordism class. And this is the question, like, in other words, like, what is the kernel of this, right? It's here, but we will need to characterize it more. So, but, okay, I want to write it out. Just so that's it. So different classes in here can correspond to the same normal cobordism there. And so now what we want to do is we want to characterize, we want to look at what this subgroup actually is. So this is a subgroup of this group, right? Because it's the kernel of homomorphism, obviously. And we want to see what it is. So 1. And I claim that this subgroup is actually isomorphic, let's see, to something I will call BP m plus 1, and this is the subgroup of those n homotopy spheres that bound some stably parallelizable manifold let's go W. So compact manifold, right? Manifold boundary. So those are just the homotopy spheres that are boundaries of some n plus 1 dimensional manifold, and we require that this n plus 1 dimensional manifold is stably parallelizable, which means that after adding some trivial bundle, well, we have a trivialization of the tangent bundle of this manifold. After that, yeah. Okay, and I will see the somehow the proof. So first, what are elements in this kernel? Well, those are some homotopy spheres with a homotopy equivalence to Sn, which are normally cobordant, well, which belong to 0 in here, so which are normally cobordant to the identity degree 1 normal length. So in other words, we have a homotopy sphere, a normal cobordism between this homotopy sphere and Sn. So this is what the normal cobordism would look like, and here the map is the identity, and here the map is the homotopy equivalence of the homotopy sphere, and how to see that such elements are precisely those homotopy spheres that bound some stably parallelizable manifold. Well, basically we just glue this here downstairs. So we have the identity in here. So if we glue this there, then we obtain this, right? Some manifold like this. And the fact that it is stably parallelizable just follows from the normal data we have here. And so I will not go. Is it okay or should I explain it?
Well, you should just like maybe explain the other way around. I mean, you're saying it's
Yeah, the other way around is just, well, if I have a stably parallelizable manifold like this, I cut out an embedded disk, and therefore I get a cobordism like this. That's what happens, right? So
And I think maybe it's worthwhile mentioning that, I mean, I hope it's obvious, but the standard sphere is in it, right? Because it's boundary of the standard disk and it's, well, it's stably parallelizable, right?
It's contractible. There's
Yeah, but in general, this is not obvious. That I mean, and in particular, we will see that not all homotopy spheres are like that. So that's a curious thing, right? That I mean, homeomorphically, topologically, those homotopy spheres are boundaries of a disk, but probably not.
Yeah.
Mhm.
And now, so we have, yeah. Now it's interesting, so what we get from this short exact sequence is an isomorphism like this. So we actually see that the normal cobordism classes, or the surgery orbits as I call them, actually correspond to the cosets of BPM plus 1 in this group. So like the orbits, the normal cobordism classes in here correspond to orbits of reaction of BPM here. Yeah, and this is interesting, right? So first of all, what we see directly is that if we have some elements of BPM plus 1, well, they are connected via some finite amount of surgery steps. So they are, yeah, we can get all the elements by doing surgery on one of them. Yeah. And so at this, so now we have two different things to do. Well, first of all, to investigate we need to investigate first of all the normal invariance. We would like to see to get a better grasp on this group in order to see what these orbits look like, and then also to investigate the subgroup BPM plus 1, and putting those two things together, but well, we would actually learn about this group, right? Okay, so let me start with the normal invariance. And it's at this moment that we will do the switching between those two views that I talked about. So I said that we have some geometrical interpretation of normal invariance and then some homotopy theoretic, and that we will switch between those two in order to achieve our goal. And so it's now that the switch happens. Okay. So let's look into it. So first of all, as I said, this is a fibration, which means that it induces a long exact sequence of homotopy groups. So we get this induces long exact sequence like this, where we have plus 1. O I D O I B T. Okay, where this definition is just the homotopy classes of maps from the sphere Sn to this space G mod O, which is just the normal invariance, right? So I will directly write it here. Okay. And the second thing I want to say is that we have an isomorphism like this. I don't want to, do I need to explain the construct over why? So these homotopy groups are actually isomorphic to the nth stable homotopy groups of spheres.
There is n minus 1.
N minus 1, yeah. Sorry. And these maps, there are some maps here, Jn minus 1, Jn, which are the so-called J homomorphisms. So this is the main thing we'll be interested in.
Well, since I mean, you could also now say that that pi and b is pi n minus 1 of O, or well, maybe you'll say it later.
I prefer doing it in that setting, since I didn't plan so far if there's time left to do the geometrical interpretation with the covariations and so on.
Mm-hmm.
And if I don't do it that way, I think I can do just fine with this.
Okay, but so if you don't want to do it, then maybe I just say, because I mean, everybody knows what O is. I mean, it's the column of these orthogonal groups, and this is obviously a space, and you can take its homotopy. Because I mean, you need to know what BO is if you. Yeah. So I'm trying to say that you don't need to know what BO is in order to understand this. And so, and if you go one step to the left, you have pi n of O. To the left. So right.
So pi n plus 1 BO, which is pi n of O.
And so that means that there is a way of producing an element in stable homotopy groups of spheres out of some element in the homotopy group of O. And that construction actually is elementary, that can be written down. You don't have time for it, but it's something that everybody can understand. I mean, like how it works. And so it's interesting because it does produce potentially non-trivial elements in homotopy groups of spheres. That's something that it's not so obvious, right? And this is one of the easiest ways of producing some non-trivial elements there. So it's interesting even outside of surgery, and that's why we have some information about it, and that's why we can then use it in surgery. So
I just write it. Anyone would like to look at it. It's called the Hopf construction. That's this.
So it's interesting also.
Not is
J.
J, or it is produced by J. So J is not between B spaces or between homotopy groups.
I don't know what people use, what sort of notation. I think
usually
it's between homotopy groups. I think.
Yeah. Well, because it's J homomorphism. So the homomorphism would.
And I think that's why he also called this J bar, the map between spaces.
Yeah, that's why. Right, exactly. That's why I call this J bar, so that it induces this J homomorphism. Okay, so we have this set up. And now I will just state some two results which will help us in using this exact sequence. Maybe we will require some black boxing, maybe not. So first of all, both periodicity, we know what are the homotopy groups of BO, respective or O, if you want. So I want 8, I, and I will write it in terms of BO. So we have 1, 2, 3, Z2, 0, Z, 0, 0, 0, and they are aperiodic, so that's that. And the second thing we need to know is about some information about the J homomorphisms, and this is actually a special case of so-called Adams conjecture, and the statement is that Jn is injective for n if n is not other than for k minus 1, n equal to 4k minus 1.
So that's on those two Z2s.
Yeah, yeah, yeah. Okay.
And yeah, your notation is Jn goes from pi n plus 1. Okay, yeah, well.
Yes, well, that's because
Yeah,
usually
right.
it's for
So it's okay somehow if anybody was wondering sort of the.
No, I'm just thinking a little bit whether I want to state the second statement about the image now or not,
But okay, so since we have some younger people here, it's worthwhile mentioning that it's known that these stable homotopy groups of spheres are finite.
yeah.
So you cannot hope to have something injective in those two other dimensions. Okay, so that's not, and okay, and then carry on, whatever you want to say. Mm-hmm.
Okay, so and yeah. Okay, so this is and so we have also some information for the case of 4k minus 1. So for the remaining case, so the image in this case is actually so has order of what is it? I can never remember those constants. The denominator of bk over 4k, where bk is the case Bernoulli number, some constant. And this is so exactly as what Tibor just said. So in this 4k minus 1 case, the J homomorphism goes from Z to some finite group, so it cannot be injective, but we have this information about the order of the image. And so yeah, let's get back.
I have a small comment. So
Yeah.
this normal invariant is equivalent to this map from Sn to Geo. Those are not pointed maps, right? So there is no base points.
Yeah. So I wanted to skip over the difference. So actually, in this case, it doesn't matter whether you consider homotopy classes of baseball preserving maps or not, because G model is path connected and simply connected. In that case, it's the same thing, right? Okay, and now so let's get back to Earth a little bit and let's see what happens in the odd dimensional cases in this exact sequence. So, first of all, for n equal to 1 modulo 4, what happens? So, let's denote this 2. So, from this exact sequence 2, well, Gn minus 1 is injective in that case, we know it thanks to this. and actually Jn in here is also injective, so we get sequence like this. 0 because of the injectivity. So this is injective, so here we get 0. This is injective, so here we get 0. And this is the exact sequence where well, n plus 1 is 2 modulo 4, so these groups are either z02 or 0. I will just write it here like this. This is z2 or 0. Okay. But what we see from this sequence, from this exact sequence, is that the normal invariance, so this map is surjective, so the normal invariants are actually equal to the image of this map by the isomorphism theorem. It's the stable homotopy groups of spheres, well quotient out by the kernel of this map, which is the image of this map, so it's just a co-kernel Jn. And since we have already shown this isomorphism, we get that so we get the first instance of what we plan to do. We reduced some part of the calculation of this group to some knowledge about the J homomorphism. So again, from the same sequence, what we get in this case, again, this homomorphism is injective. This one is no longer injective, but okay. So far that doesn't bother us. So we know that this group is that, and we get the same isomorphism as here. So in this case, again, normal invariance isomorphic to the co-kernel of the J homomorphism. So now we finish investigating these normal invariants. We need to learn something about Bpn plus 1. But let's put that aside for a while and let's look at the even dimensional case, and we will see how this comes out of this even dimensional case. Or actually, let's first look at the case where n is equal to 2 modulo 4. So from the sequence number 1 in here, from the surgery exact sequence, again, it splits into some shorter sequences. Now we are in the even dimensional case, so these groups on the right side will be non-zero, but the group here on the left will be zero. So get an exact sequence like this. This group will be Z02. So this group will be Z02, and the image of this map will be the. So yeah, let me show you here. Alright. Okay, so the map would go here to theta n minus 1, and the image of this map is the kernel of the map before it, so therefore it's just this BB, right? Okay. And furthermore, I said that in the case 2 modulo 4, this isomorphism of L groups with Z mod 2 is given by the ARF invariant. So here actually this map will be the ARF invariant of the normal 1 degree map here. Degree 1 normal map, sorry. And in this case it's called the Kerber invariant. Right? So Kerber invariant. And so see that in this even dimensional case the problem is of a different nature than here. So yeah.
So if we consider that, okay, can you give the board out to me?
Yeah.
L for k plus 2 is just Z mod 2.
Yeah.
Yeah. So as Z mod 2 map to Z mod 2, does it map like switches like 1 to 0, 0 to 1?
What do you mean Z mod 2 map? Z mod 2? This expresses the fact that this is Z mod 2. So this is the.
So that isomorphism is that isomorphism on
Yes,
the
yes,
left?
yes, 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 yes.
Okay.
That's what I just wanted to say here, that these isomorphisms here are
Okay.
given by those maps. And this map actually, when you put it in the exact sequence, so when it comes from the normal degree 1 normal maps, it's called the Kerber invariant. And in here the problem is of a different nature. So now actually different classes in here do correspond to different classes in here, so the different elements of 2 different classes in here cannot be connected by surgery steps. In other words, this map is injective, but we have a non-zero surgery obstruction, so not every degree 1 normal map comes from homotopy equivalence, right?
Possibly non-zero. You
Possibly
don't know.
non-zero, possibly non-zero. So, okay, let's see if I want to say something else. Okay, and so we can see from this exact sequence that first of all we see that in this case BP n plus 1 is, well, trivial, right? Because this map is injective. We see that this group corresponds to, well, it's isomorphic to the kernel of this surgery abstraction map, the Kerber invariant map. But we also see that here on this end of the surgery exact sequence, we get BBN, so actually what the thing that interested us in the odd dimensional case, right? So this is what we wanted to calculate. And BBN is isomorphic to the co-kernel of the Kerber invariant map. And so what is left to do is, it's not an easy task, but we see that by investigating this Kerber invariant map, we will actually learn the things that we,
It might be good to give it an index to, I mean, KIN.
yeah. And okay, and so especially what we see. So this is a map that is into Z02, so we have only two possibilities. So either it is surjective or it's the zero map, and this is actually the so-called Kerber invariant 1 problem. So, which is a problem in homotopy theory for many years, and the question is, does there exist a manifold in here that has Kerber invariant equal to 1? So that's why it's called the Kerber invariant 1 problem. And up to now, it's been resolved in every dimension except 1. And in every dimension except 1. And okay, maybe not in a theorem. I will just state that what are the results. So it is surjective only for n in n here. So 2, 6.
Yeah. 14, 30,
30,
62.
13, 30, 62, right? 14. And it's the zero map for all other n except possibly n equal to 126. This is the only unresolved case that's left, and so yeah.
Why are these round numbers are so random?
No, they're not. I mean, so the
Powers of 2
2 power n minus 2.
it's a power of 2 minus 2, and so the reason why it's surjective for 2, 6, and 14 is complex numbers, quaternions, and octonions. The 30 and 62, that's harder to say why, but people found manifolds with this Kerber invariant 1, and then in all other dimensions. So first it was proved that in dimensions other than 2k minus 2 it's 0. That's already, I think, 1969 by Browder. And then it was a long standing problem, and it was solved. I mean, it wasn't this solution was announced in I think 2008 and published 2016 by Hill Hopkins Ravenel, that all these 2k minus 2 beyond 254 254 and beyond, it's also 0. So that was a big deal, but by completely different methods than this. It was just very sort of homotopy theoretical, but it's the upshot is geometric in the sense of some. So there's only one case open, and that's the one. Yeah. Mm-hmm.
Okay. So there's that, and now let's look at the 4k dimensional case. And I have to think about what I want to do. And so again, let's see what comes out of this sequence from 1. Well, we are in the even dimensional case. We will get almost the same thing as there, just the algorithms will be different. So 0, and I will write 4k. That BP for k 0. Where now this map is taking the signature of the manifold in here, dividing it by it. Okay. And so in this case, the problem is of the same nature as there. This map is injective, so we have no BP for k plus 1, it's 0, but there is a surgery obstruction which is possibly non-zero. And again, we see that here that this group that interests us of homotopy spheres actually corresponds to precisely those manifolds in here that have 0 signature, and BP for k So again, we need to investigate the signature a little bit more to find out how does the group of homotopy spheres look like. So at this point, let me digress a little bit. I need to talk about Pontryagin classes. I need to explain what are Pontryagin classes. The Pontryagin classes, Pi, so far let me denote psi, are some elements in specific elements in the cohomology groups of a manifold, which depend on some bundle over the manifold. So given, in other words, given elements, specific classes, corresponding can I say corresponding to a bundle?
Associated to a bundle. Or,
Huh?
I don't know, associated to a bundle. Oh, yeah, I mean, you can say, yeah.
Yeah, associated is better.
That doesn't matter. It's
Okay, associated to over M. Right. So the situation is we have some vector bundle over M. To this vector bundle, we assign cohomology classes in the base space, so in the cohomology of the manifold, in each fourth degree. So in zeroth cohomology class, fourth cohomology class, and so on. And these classes in some sense, let me say measure to what extent to what extent is this bundle twisted? Okay. And yes, so what else is important is that the Pontryagin classes are stable isomorphism invariants. So in other words, if I have two stably isomorphic vector bundles, they will have the same Pontryagin classes. The opposite way, it doesn't work the opposite way. So if two bundles have the same Pontryagin classes, they are not necessarily stably isomorphic. And they have a nice naturality property. This so if I have some bundle map between two bundles and possibly different manifolds, then well, then I get this kind of equality in
well, bundle map means that eta. Well, bundle map means that eta is isomorphic to the pullback of xi.
Yeah, right.
So that's
so I get this kind of equality in the cohomology group of N. So yeah, we have some natural property, and lastly, let me say that we'll be talking about sometimes okay, let me just say this. If someone says the Pontryagin classes of a manifold, what is implied automatically is that these are Pontryagin classes of the tangent bundle of this manifold. So they always depend on some bundle, but if I say Pontryagin class of M, it's implied that it's the Pontryagin class of the tangent bundle. Okay. Maybe they let me give a quick alternate definition or alternate view point. Those Pontryagin classes. Or the description. So the Pontryagin classes actually are correspond to or are a natural transformation between the functors the O, which takes topological space to, well, let's say the set of stable isomorphism classes of vector bundles, and the cohomology functor, which again takes it to set composing it for functor, let's say, right? So this is just the someone prefers category theory language. Okay. Okay, now at this point I want to prove a lemma. So I want to take a look at how do the Pontryagin classes look like for elements in here, for manifolds in here. So for manifolds for which we have a degree 1 normal map. The lemma says that if we have a manifold from normal invariance, then the Pontryagin classes of these manifolds, which mean the Pontryagin classes of the tangent bundle, are all 0, except possibly well, of course, for I equal to 0, in this case the Pontryagin class is always equal to 1, but this is here, and except possibly I equal to k. Okay, so here I had to write for k. So all the Pontryagin classes of these manifolds are 0 except the highest one in the 4k dimensional cohomology. M is of dimension 4k. Okay, and how do we prove this? Well, it's not hard to see. So first of all, it's obvious that.
Well, what do you mean? I mean, the cohomology is only non-zero in those two dimensions, so it's obvious.
Sorry?
It's totally obvious. Oh, sorry, of n. Sorry.
It's from the normal invariance,
sorry.
but it's not much harder. It's just that so. So for any bundle over the 4k dimensional sphere, obviously this holds, because the cohomology of SK is 0 on this. I equal to, unless and the second step is just using the naturality property of Pontryagin classes together, right? So if this is from, this means that we have a bundle map this, and that implies that the Pontryagin classes of Pm plus Ra equal what's the Ubek by f of Pi psi and Pontryagin classes are stable isomorphism invariants, so this is Pi, Pm, and so this is 0 for I different from 0 and k, so this is 0 for I different from 0 and k. And now comes the important point. Why are we interested in these Pontryagin classes in all this story? It's because of one result known as the Hirzebruch signature formula. Which states that the signature of 4k dimensional manifold can be expressed as the evaluation of some the evaluation of something on the fundamental class of M, and where this something is just a polynomial in the Pontryagin classes. Right? So each Pontryagin class is some cohomology class, so we can evaluate it on the fundamental class. This is some polynomial in them, so we get a well-defined integer. And the Hirzebruch signature formula states that this is equal to the signature of the manifold. And do I have to say something about the proof or whatever? The idea.
No, but I think it's more important maybe to say that it's a polynomial with rational coefficients.
Yeah. Okay.
So, and it's interesting because well, the whole point of this business is that a priori the right hand side is only a rational number, but because it equals the left hand side, which is an integer, it's an integer. So that's and about the proof, some seminar, some future.
Yeah, the idea.
But yeah, I mean.
And yes, so and actually this point that Tibor said that the coefficients are rational numbers, but the total result is an integer. This is what leads to the discovery of exotic spheres. So for the first time by John Milner. So this is actually where he spotted some, let's say, contradiction. Okay. So and now see that from lemma 2 in our case, this equality simplifies a lot, because actually all the Pontryagin classes are 0 except the highest one. So this polynomial will be very simple. And so for M belonging to the normal invariance, it's actually the case that only the highest Pontryagin, the kth Pontryagin class figures here, and the coefficient by which it is multiplied is sk, which I will tell you what it is. It simplifies to this, where sk is 2 to the k minus 1 over something. some constant where the case Bernoulli number again shows up. Okay, so we have this formula for the signature, and so let me just write again here that the signature was some map from the normal invariance to Z, given by this. And so now again we would like to switch, I'm pointing to nothing, it's not there anymore, to switch to this homotopy theoretic view again. So we would like, so far this map is formulated in this view where we have normal cobordism classes and degree 1 normal maps. But we would like to switch to a point of view where we have this map as a map from the homotopy classes of maps from Sn to Gmodo. So the nth homotopy group of Gmodo. And what's the difference? The difference is that here we had some degree 1 normal maps, and the signature, this map was formulated in signature of the manifold M. Now here we only have, I talked about that just last time, I didn't mention it again, but those are pairs of just vector bundles over Sn and some fiber homotopy trivializations of these bundles. So now we need to express this map as actually a map involving this bundle over the sphere and not involving some manifold which is here. And we can do this switch easily thanks to the naturality properties of the Pontryagin class. How? Well, okay, so this is equal to this. But now, thanks to the fact that F is a degree 1 map, the fundamental class of M is the what I want to say. Oh, so no. So I need to use the fact that it's a normal map. So right. So thanks to the fact that this is a normal map, so we have this bundle data. Then this TM stabilizer is actually the pullback of this bundle, right? So we can see this. Yes. And by the naturality of the Pontryagin classes.
PK.
PK, right? Okay. And now, well, it's not hard to see that. this is just oh yeah, the relationship between like this
Yeah, that's a formula.
evaluation with the-
That's a formula that always holds. Yeah.
right, and now thanks to the fact that f is a degree 1 normal map, this is just the fundamental class of Sn. So we get a formula like this, and so now we have something that we can interpret as coming from here. So what we see right away is that the formula depends only on the vector bundle side. So we don't care about the, for example, the homotopy trivialization in here. So actually the map in, and I'm just thinking, how should I call this map? And so we can see this map as a composition of first a map into BO, so just taking the vector bundle,
Mm-hmm.
and then a map in here.
Mm-hmm.
And I will call this map EK if it's okay.
Oh, that's not good because
Okay,
it's the
Montreal class.
but I don't know how should I.
Yes.
It's called
EK, is it okay or? Okay, doesn't matter what I call it.
completely different letter. I don't know, some alpha or something like that.
Or you can put heart shape there.
Alpha K.
Okay.
So that's the map that takes psi and does skpk and evaluates, right?
Yeah, right. Right. And I'm just thinking, how should I say this? So furthermore, we know that this group is actually Z.
Mm-hmm. Because it's 4K, it's by 4K, it's not.
Yeah, right. Thank you. Because it's 5 4K. Okay, so this is Z. So we have a, I will write it here. We have a specific isomorphism into Z. I will call it phi.
Mhm.
And now the question is, what's the relation between these two maps into Z? Or
Mhm.
in other words, what should I put here in order for this diagram to commute? And okay. And this will, okay, let me just state it as a result. So
Yeah, mhm,
it's,
sure.
it's known the relationship between
Yeah,
this isomorphism phi and the
Mhm.
Dragon class map. And this map is just multiplication by sk times dk over 8, I think.
Mhm. And so I'm thinking very confused. Yeah. AK times 2k minus 1 factorial.
Yes. AK times 2K times 1 factorial.
Yeah, right. So that's related to SK. I don't know. Do you have SK still somewhere?
Yeah,
Yeah, but the what it is you wrote down somewhere.
yeah, I have it.
It's, the
2
fifth
power
level.
k minus 2.
Yeah.
All right. So and AK was
AK was either 2 or 1, I don't know, how was it?
0 or 1, I think. If k is up.
3 minus 1 to the k over 2 or something like that. It was either 2 or 1, I don't know. It was something.
okay. Fair enough.
Time constants. Some constants. What is important is that this map is injective. Actually, this is the important thing. And
Well, several things. So maybe okay. So you just sort of said it as a black box, but somehow to put some ideas into this is that map phi. So that's actually something that realizes that isomorphism of pi for kb with z that was known to be in terms of the case contractness, right? So that somehow it can be calculated in terms of that. And if once you have that, then it's just a matter of calculation what exactly this map is, and so somehow yeah, okay. So it's known, and we take it, and it's known because that calculation can be done in that way. So it's important that it's injective, but not only that, it's important that we exactly know what it is, right? Because we are interested in the image.
Yeah.
Right. So we are interested in what is the image of the signature over 8.
yes, for the
And okay.
yes, but so far so let's first focus. So remind that we were interested in the kernel of the signature for
Cool.
no, also in the kernel for so
Yeah. Right.
Where
Sorry.
is
Yeah.
it?
Both. Yeah.
here, yeah. So in the kernel, in order to calculate the 4K homotopy, the 4K group of homotopy spheres in the co-kernel in order to calculate BP. But so if we are interested in the kernel of this map, in other words, which manifolds in here have 0 signature, well, since this map is injective, this map is an isomorphism, it boils down just to being interested in the kernel of this map. In other words, we know that all vector bundles over the sphere, so two stably isomorphic, two vector bundles with different contracting class cannot be stably isomorphic. This is injective, so it remains to see which elements in here map to the same bundle in there. Okay. So we see that the kernel of this. Yes.
Okay. But now you can quickly see it from what you have there,
Yes,
right?
Yes. And now this map is this map in this sequence. So from the sequence 2, we get that the kernel of this map is equal to the image of this map, which is just this group by the kernel. So this group by the image of here is the co-kernel of the J. This is the kernel of the signature. It's the surgery abstraction map, so it's we get that.
And again, right, so this is something that is somehow we can't express it in terms of these point classes somehow. It's something. Okay.
Okay, so even in the for k-dimensional case, again we see that we get the isomorphism with the co-kernel of J, even if the problem was of a completely different nature. Somehow it works out this way. Yes, and now the second thing we were interested in is the co-kernel of this signature map. So the co-kernel, which is just the module image of this map. But by commutativity of this diagram, we see that this is actually here the module of the image of this composition. So something like this. Yeah. But phi is an isomorphism, and so okay. Let me rephrase this as saying that this co-kernel is isomorphic to a finite cyclic group of order co-kernel of even better sk times dk over 8 times co-kernel of phi composed with this delta. But phi is an isomorphism, so the co-kernel of this is actually the order doesn't change if I give out phi. Is it okay or?
Yeah. Okay, so now the question is, what is the co-kernel of this map? And again, from the exact sequence here, you see that the co-kernel is well, it's pi and bo by the image of this map, which is pi and bo by the kernel of this homomorphism, which is isomorphic to the image of this homomorphism. Sorry,
by the
just
isomorphism.
Yeah, right, okay, yeah.
So this is actually just finite cyclic group. Of order sk times dk over 8 times. Okay, I should have just. Right. And we know what is the order of this image from here. Is the denominator of the quotient we have there. So it's actually, this is isomorphic to, well, all those constants together, right? Do I have to?
Yeah, well, it's okay, it's here, it has to be calculated, so some numbers, yeah.
Yeah. So we know that the order of this image is the denominator of this, and then we just get, what it is. We get some constants, and is it maybe what is the result? If I calculate all the constants.
Okay, well, ak times 2 to 2k minus 2 times 2k
Okay.
2 to 2k minus 1 minus 1 times the numerator of that.
Okay, I thought it's simple. Okay.
It's complicated. I was trying to looking for a table that would say what it actually is for some values, but I think the this is bad. There will only be very few. Hold on, I'm looking for the table still.
So BK will cancel each other or not really?
Well, no, I think it will just.
Sorry,
There
what are you asking? What will cancel
Whether
what?
BK will cancel each other, no, but because there is just the denominator, so the effect will be that in the resulting
There will be
you'll have the
numerator.
numerator of.
Yeah. Yeah, right. So, okay, so it's some complicated constant, but at least we can say the first three interesting values, right? So for k equal to 2, one will get 28. So that's the 28 7 spheres. Then for k equals 3, one will get 992. And that's
Okay, maybe.
and then in number for k equals 4 in dimension 15 one will get 8128.
Okay, I will maybe write it when I summarize.
Mhm.
So yeah, we find out what the co-kernel of this abstraction is, and why was it interesting? Because well, it's what gives us this pp4k, separate pp4k. So yeah, I will just write it here.
Can we know like what those elements in those cyclic groups represent which homotopies in geometry?
Well, that's all depends. Like, what do you mean by no? I mean, like if you want explicit, there are explicit constructions, but I think not of all the elements. There are. It's an interesting problem. How do you represent which? So there's one. It's one thing to have abstract calculation that this group is that and that, but another thing is how do you construct elements that represent. How do you construct those homotopy spheres? And there are some constructions, but I'm not completely sure that.
Given a particular homotopy, so can we decide where in which class does it land, in which this element will it land?
So that's another question. You're looking for invariants, right? So I was.
Zero corresponds to the standard sphere.
Yeah.
And do they know the generator?
Oh,
Well,
it's not necessarily cyclic.
Well, the BP is cyclic, right?
Uh-huh.
That's
But
Okay.
So I don't know I mean, there are these Briskon spheres. I think the Briskon spheres are in BP, right?
yeah.
And do they give all the elements in the BP? I'm not sure. I don't know. So that's one thing. But I think Sergey was asking a different question. How do you detect homotopy spheres? I think that's a lot harder. There are invariants, but it's not so easy. It's tricky to figure out. I mean, in this our book there is something about it at the end, but I forgot. I mean, we quote some results, but maybe we talk. You should finish and then maybe I'll.
Yeah. Now I will just summarizing. So first of all, let's look at BPN. So what did we find out? So we the subgroup BPN is 0 for n odd. No, for n, yeah, odd. Then if if n is 0 modulo 4, it was the case that we studied just now. We saw that it's okay. So it's a finite cyclic group of some order, and so, for example, BP 8 is isomorphic to ZMOX 28. BP 12. What did you say was 992?
992.
992, right? Z992. Then BP 16 was Z1000.
No, 1 to 8.
Ah, yeah, 8. Okay. The order of those groups grows really fast. And it was either I'll write it like this: Z2 or 0 for n equal to 2 modulo 4. And actually, do I have it here somewhere? I erased that. So, why? Because it was given by the co-kernel, the Kerber invariant, which went into Z02. So if the Kerber invariant was surjective, then the group is 0. If the Kerber invariant was 0, then the group is
Yeah,
Z02.
and I think so. It's a good time to say better answer than to your question. So the you can construct these by the plumbing construction. That's more elementary. So the standard plumbing construction constructs generators of this BPN. That's sort of obvious from surgery, and but it's also true what I said, that you can construct by Briscoe spheres.
All of them.
I mean, it says here
Okay,
about
okay.
that you can do generators, and then yeah. So I suppose yeah, I don't know. So yeah, it seems that the element, the exotic spheres here, there are good constructions. Maybe I think it's probably harder with the other, with those that are in theta and modulo BPN.
And so actually, since you know this is the co-kernel of the Kerber invariant, I can actually make this statement a bit better, because I had already a statement about what the Kerber invariant looks like. And so this is 0 for n in what 2, 6, 14, 30, 62, and it's Z02 for n till other n, except possibly. Six, right? So please just follow directly from the statement we had for the Kerber invariant. Okay. Now the second statement I want to make is about this quotient. Okay, so these will be two statements. So first of all, we saw that this group is isomorphic to the co-kernel of the J homomorphism for and different modulo for and for n equal modulo for n equal to 2 modulo 4 we had a short exact sequence. Like this. So 4k plus 2. 4k plus 3. Co-kernel J plus 2. And here we have 2. And
Mm-hmm.
so actually I think I didn't finish the case with this with showing this. So I said that this is isomorphic to the kernel of the Kerr invariant. But
Yeah, well,
okay,
that's
okay, this
clear
this
that
holds.
that yeah.
So in this case, it's also it's isomorphic to the co-kernel of the J homomorphism, possibly up to some
Mhm.
z-2.
Yeah. Mhm. Yes. Mhm. Okay.
And so in the even dimensional cases, I wrote it that way just to see the correspondence, but in the even dimensional cases, actually this is 0, so this is just the theta n.
Okay, great. So I think
So it's 4k plus 3 or 4k plus 2?
So this BP, it's always denoted BP n plus 1 because just to allude to the fact that it's the boundary of an n plus 1 manifold, but it's actually a subgroup in theta n. So here it's 4k plus 2, here it's 4k plus 3, but
But
it's the 4k plus 2 case.
Yeah, but it's trivial in that case.
Yes, so BP is trivial for odd n.
so you didn't have to write it there.
Yes, I didn't have to write this, I just wanted to show the symmetry between
Yeah. Mhm. Okay, so thanks. So I think